Hello everyone. So today let's solve the problem Dirty Arcady's Kitchen. Right. So this was asked in the Codeforces Round 4 to 3 for the Division 1 rated based on the VK Cup finals. Right. So you can just go through the question. It's easier for us to solve the problem. Uh, so that this one I'll summarize the question, right? So that it will be easier for us to solve the problem. Right, so let's see what the question states here. So there is a guy named Arkady. Just give me a second here. There is a guy named Arkady, right? He starts at node 1. So let me give here n1. Arkady starts at, so I'll just give here a. Arkady starts at node 1 at time 0. At time 0, right? And he wants to reach node n as early as possible. And he wants to reach the time n as early as possible. Each undirected edge, each undirected edge, just write u here. Each undirected edge here, suppose if we consider this one undirected edge as a and b. So each undirected edge a comma b is usable only during the integer time moments, right? Integer time moments in a given interval L comma R. In a given interval L comma R. So traversing any edge takes exactly 1 second. Just remember this one. Traversing any edge, right? So while traversing any edge takes exactly 1 second, man, right? Exactly 1 second, right? And we cannot stop inside an edge, and we cannot stop inside an edge, right? So what we need to do here, what we need to find here, we need to find the earliest arrival time. So we need to find the earliest arrival time, right? So just give me a second here. We need to find the earliest arrival time, right? At the node n, at node n, and we have to print -1 if it is impossible, and we need to print -1 if it is impossible, right? So this is the question. Basically, let me read the question loud. Just listen to this carefully. Arkady starts at node 1, right? Arkady starts at node 1 at time 0, and he wants to reach node n as early as possible, right? Each undirected edge a comma a comma b is usable only during the integer time moments in a given interval L comma R, left comma right. So right, so traversing any edge takes exactly 1 second, exactly 1 second, and we cannot stop inside an edge. And what we need to find here, we need to find the earliest arrival time. So what we need to find, earliest arrival time at the node n, at the node n, and we have to print -1 if it is impossible to find the earliest arrival time, right? So this is fine, I believe. So this is it for the question, right? So let's move on with the input output part. See here, we have been given nm, right? So we have been given n and m basically, and we have a number of nodes. We have 5. Dem we have been given 6 here, right? So we have 5 nodes here. You can clearly see here 1, 2, 3, 4, 5, not more than 5 nodes, right? So you can clearly see here, and we have m which is equivalent to the 6. So the earliest arrival time at the node n has to be here 3, right? So the output is 3. Same goes with here for the example 2 as well, right? So it is impossible here. So we are returning -1. This is fine, I believe. Now, we are familiar with the question and the this one. What do we call? Input output, right? So let's do one thing. Let's quickly discuss the approach followed by the complexities, and then let's write the code. As usual, let's discuss the approach first. So I have considered the same first example within the question here, right? So here we have 5, 6 that just we have been given here, and the output that we need to get here is this one, 3, right? So this is fine, I believe. Yeah. Now, yeah, let's move on with a step-by-step explanation. First, what we'll be doing, we will be expanding each node into 2 parity states, right? So this will be going with a Dijkstra kind of structure. So basically what we'll be doing, so we'll be going with a parity states, right? Parity states approach basically, right? We'll be going with a Dijkstra kind of structure, right? So just remember this, we expand each node into 2 parity states, right? First one is just node, and the second one we can just consider node plus n, right? Node plus n. In our case, it is 5. We have been given n equals 5. Node and node plus n, right? So to model the arrival at even or odd times separately. That is the reason we'll be going with it. This is fine. For each original edge left comma right, we create up to four directional intervals, four directed intervals or four directional intervals, right? For each original edge L comma R, we create up to four directed intervals between the parity states with the adjusted integer types, so that starting time parity matches the edge availability, and traversal uses exactly 1 second, and the traversal uses exactly 1 second, right? So this is fine. We run a digital-like process on the states, always taking the earliest possible departure. We'll always consider the earliest possible departure window from the node state. Just remember this one, right? Whenever an interval, this one intersects, so if the interval, suppose if the interval intersects our current reachable window, we push the this one, our current reachable window, we push the next reachable time window for the neighbor, right? So, right, from a node state, whenever an interval intersects, right, our current reachable window, we push the next reachable time window for the neighbor. So that's what we will be doing. So this will be understanding this one clearly when we write the code. Just remember this one, right? So we try to implement the same thing in the form of code. In the sample, so in the sample, in the sense, in the example that we have considered this one, right? So 1 2 2 5 2 5 twice 1 3, this one 1 3 3 4 and 4 5. So in the sample at node 1 time 0, we follow available intervals here with a matching parity and propagate earliest reachable windows until node 5's this one parity stated is reached at the time 3, is reached at the time 3. So concretely we can consider here 1 to 2, 0 to 1, and then 2 to 5 at the 0 to 1, at 0 to 1, or 2 to 3 also, right? So we can consider, or 2 to 3 as well. Concretely, we can consider 1 to 2, 0 to 1, 2 to 5 at 0 to 1 or 2 to 3. So the algorithm examines intervals and finds the earliest arrival at the node 5 is time 3. So we have got time 3 for this one, right? So the output that we got here is time 3 or 3, which is equivalent to the output that they have mentioned for the example 1 within the question. So our approach works absolutely correct here. So as we are completely familiar with the approach, let's do one thing. Let's quickly discuss the complexities part, right? So what will be the time complexity here? The time complexity would lead to big of n plus m logarithmic m, right? So the time complexity would lead to big of n plus m log m. And what would be the space complexity here? The space complexity would lead to big of n plus m, right? So why the time complexity is big of n plus m logarithmic m here? So we will be sorting all the interval lists. So where total intervals is less than or equal to 4m, right? So we know this one, 4 minutes basically. Plus processing each interval once with the priority queue operations, right? So we'll be going with a what do we call? Processing each interval once with priority queue operations, that is dominated by m log m, right? So overall it would be big of n plus m, big of n plus m log n, log m, sorry, right? The space complexity will store up to 4m interval, this one entries and auxiliary arrays of size that is equivalent to almost equal to 2n, right? So overall space complexity we can give big of n plus m, right? So time complexity and the space complexity for the code that we'll be writing in the future would be big of n plus m log m and big of n plus m respectively, right? So now as we are completely familiar with the approach and the complexities, we are good to write the code. Let's start writing the code. So let's start writing the code here. So first we'll be making use of the fast input and the output along with the different utilities, right? So let's import the input output package as well as the utility package. So I'll just go with java dot uh, input output dot stuff. So this is fine. Also, let me go with java dot util dot start. So this is fine. Now let's go with the class main. So within the class main, what we'll be doing? So let's initialize certain things and let me explain also the helper method, the small helper method. So let me paste this one over here. So this one static final intent equals whatever I have written here. So this is the constant for the maximum array size, right? So for the safer side, we have considered plus 5. This is fine. Yeah. Now static intent m. N is nothing but the number of nodes and m is nothing but the number of edges, right? So here number of nodes, this one 5 in our case, and number of edges is 6 here, right? So this is fine, I believe. Yep. Now static, this one is fine. This position, which is of the size, this one new int of n, whatever I have given. So position of x pointer into the sorted adjacency list, right? So this is fine. Now array list, so this is nothing but the adjacency lists, right? Adjacency list. So this is fine, I believe. Next, let's move on with the helper method work, right? So this is the helper method just to add an interval edge from x to 5, x to y with a integer time window left to right. So we have discussed this one in the approach, right? So don't get confused here. So now here I'm going with if left is less than or equal to r, v of x dot add, we are adding this one, new int of l, r, and y. So what is this basically? So we are only adding if valid interval, right? So we are just storing start, end, as well as the destination. Start, end, destination is nothing but left is start, right is end initially, and y is nothing but the destination, right? So this is fine, I believe. Next, let's move on with the main method, man. Yeah. Just give me a second here. Yeah, I'll just go with here throws input output exception. This is fine, man. Yeah. Within the main method, so let's do one thing. First, let's write the code that's related to the input output, man. Just give me a second here. So let me come here. Let me copy paste the this one. What do we call? Just input output related things. Then we can just type the this one logic, right? Main logic. So this is purely related to the this one. What do we call? uh, Input output related things, right? So buffered reader, so this is the fast input. Let me explain this one very quickly, right? So this is the fast output print writer, and string tokenizer is nothing but it reads the first line basically. That is the reason we are making use of the string tokenizer here, right? So, and we have to pass this one, not pass basically, we have to parse n and m, right? So this one I'm speaking of. So this is nothing but n, this is nothing but n, right? So we have to parse, right? So 2, 1, 2 is n and 1 is m. So we have to parse that one. We are just passing this one, right? So this for loop here, so this is for the adjacency list for all the 2 into n states from 1 to 2n, right? From 1 to 2n. So we are just initializing the adjacency lists for all the 2 into n states from 1 to 2n, right? So now this priority queue, so this priority queue stores the current reachable window states, right? Start time, end time, and the node start. And we are making use of the comparator as well. If you see here, we are making use of the comparator here. Comparator, this one, what do we call? It priority queue makes use of the comparator by start time ascending, right? So just remember this one. So this one q dot add whatever we have written, we are starting from the node 1 at the time 0, right? So this is fine. Next, let's move on with the for loop here. We are just reading the edges and transforming them into the directed usable intervals between parity states. So that's what we are doing. That's what we are doing here. So x, y, l, and r here. So this one endpoint a, b, as well as available interval start, that is inclusive, and available interval end, that is exclusive, L and R, right? So we know this. Next, let's move on with the logical part, right? So let's go with this one. What do we call? For an undirected graph at x comma y available on the integer times t with less than this one L less than or equal to this one t greater than or equal to L less than R, we may attempt to start traversing at the integer t and arrive at the t plus 1, right? So basically we'll be making use of the parity splitting trick here, right? So we'll be going with a node and node plus n, if you remember the approach when we discussed that one, right? Node and node plus n, which represents even or odd arrival, this one parities, right? Again, I'm telling we'll be making use of the parity splitting trick here, which is similar to the Dijkstra structure. So we'll be going with node and node plus n, which represents even or odd arrival parities. Then we can create up to 4 directed interval edges depending on the parity alignment. So let's create that this one for directed interval edges depending on the parity alignment now. So I'll just go with here work x comma y plus n, node and node plus n we have to go with, right? So this one has to be L plus L bitwise and 1. So this is bitwise and 1. This is fine, comma. This one r and 1, r and 1, if it is equivalent to 0, then we'll be displaying 1, else we'll be going with a 0, right? So this is fine, I believe. Next, let me copy paste the same thing here and make the necessary changes for the next three. This is fine. So this will be instead of x, it will be x plus 1. So instead of y plus 1, this will be y itself. This remains same actually, right? L plus L bitwise and 1. Um, this one, this remains same. What this one remains same, right? So this one we have to change here. So here, let me remove r. So if it is equivalent to 0, then we will be displaying 1, else we'll be going with a 0, right? So then we can just give r here. So here r minus r bitwise and 1, right? So this is fine, I believe. Yeah, next let's go with x. So this one y first actually. Y, this one will be x plus 1, right? So this is fine. So the second one is from x plus n we are considering, right? From x plus n to y, this one, the second line from x plus n to y. So we are checking for the other parity basically. We are shifting the start parity by 1. The third one, we have to go with the symmetric for the reverse direction y to x, right? So we are going with the third one currently. So this one will be y x plus 1. This is fine. L plus L bitwise and 1, this remains same actually. So this has to be um, r minus r bitwise and 1, which is equivalent. If it is equivalent to 0, then we'll display 1, else we'll be going with a 0. This is fine. The final one, so work y plus n hit has to be. So here this one has to be, sorry. So this one has to be y plus n. In the place of y plus n, it will be x. This is fine. L plus L bitwise and 1, this remains same. Here, let me remove this one. If the value is equivalent to 0, then we are displaying 1, else 0. This is similar to the this one, second one. Here, we'll be going with, what do we call it? R minus R bitwise and 1. This is fine. Yeah, let me come out of this one entirely. Now, as per the approach, we have to sort the interval lists by the start time in the ascending order, right? So we can sweep through them using the position of x. Let's do that. Let me go with the for loop here. Equals 1, I less than or equal to n into 2. So this will be I plus plus, right? So this one will be v of I. This is fine. Dot sort. This is fine. This is comparator. Mm, so this one will be comparing time. So not the time actually. Comparing int we have to go with, right? Integer basically. So a, we go with a of 0. This is fine, man. Yeah. Now let's go with a Dijkstra kind of structure, right? So this is fine, man. So yeah, first go with a standard while loop, right? Standard loop. So this is nothing but Dijkstra like sweep over reachable windows, right? So I'll just go with while not of q dot is empty. So this is fine. Now let's get the earliest start reachable window. So this is nothing but int current equals q dot poll. This is fine. Yep. Int L equals current of 0, and then R equals current of 1, and X equals, so this one, current of 2. So this is fine. Uh, this is fine, man. This is just the initialization part. All we are doing here is we are getting the earliest start reachable window, as well as we are assigning this one, initialization. L equals start, R equals, and uh, X equals this one, node start basically, right? So now let's move on with the if condition here. If we have reached either parity of node n, then we have to go with the earliest arrival time, that is nothing but the this one L, right? And then we have to terminate the code. So that's what we have to do. Let's write the simple if condition here. So this is fine. If value of the x is n, value of x is equal to n into 2, then I'll just go with out dot println. So this is fine of L. Yeah. Now I'll just go with out dot flush here. So this is also fine. Next, let me give return here. We are just terminating the program. So let me come out of this one entirely. Now for the current node state x, let's process all the intervals with a start less than or equal to r. One more while loop here. So while, so this one position of x actually, if it is less than u of x dot size here, this is fine. V of x dot size, this is fine. And v of x dot get here of position of get position of x, we have written, right? Position of x, then 0, this is fine. If it is less than or equal to r, then what we need to do here, we have to go with e equals nl nr, nothing but the left, right, as well as the destination y, right? So I'll just go with int here e. Let me assign this one to v of x dot get position of position of y, position of x we have to give here, sorry, not the, this is fine. Next, as I've said, e is equivalent to nl nr and y, right? So let me go with nl equals e of 0 and nr equals e of 1, and finally y equals e of, this is fine. The next step would be, so let's go with a simple if condition. When there is an overlap between L and this one, NL and NR, right? So if suppose NR is greater than 1, then what we need to do, we have to go with the earliest departure time inside the overlap. So NL, let's assign this one to the math.max of NL comma L, right? So this is fine. The next step would be we must start strictly after NL minus 1, right? So this one I'll just go with NL. Also, we have to go with the arrival window that becomes NL comma NR effectively, right? So this one will be plus NR. This is also fine. Finally, we have to push this one new reachable window for the neighbor state, right? So this one I'll just go with q dot add. This is simple. Yeah, new int. So this is fine. I'll just go with NL comma NR comma destination by. So this is fine, man. Now let me give semicolon here. So let me come out of this one entirely. So we have to advance the pointer for the excess intervals, right? So let me increment here position of x plus plus. So this is fine. Let me come out of this one entirely. We are done with the code. All we have to do is if the priority queue gets exhausted and we are we have never, suppose if we have never reached node n, then we have to print -1 in that case. They have strictly given in the question. So I'll just go with out dot print ln of -1, right? So finally we have to flush the output. I'll just give here. You can just make use of out dot close or out dot flush. It doesn't matter, right? So we are done with the coding part. We are done with the coding part. So before checking the code with the different inputs, let me do one thing. Let me copy paste the signature starter template here. Just give me a second. So let me paste this one over here. So this is fine. Uh, Now let me come to the question. Let me copy this one. The output that we need to get here is 3. Let's check the same here. Semicolon expected. So we are going with the comma itself, right? Line number 52. Do this one. So we have given here semicolon I have given here. This is fine. Walk of x plus n we are considering y comma l as well as this one. Plus we are going with, oh yeah, this one I have to give here one more this thing. What do we call? Mm, parenthesis actually. Yeah, this one L bitwise and 1. If it is equivalent to 0, then we are displaying 1 or then we are printing 1 else 0. Right? So this is fine man. R minus R bitwise and 1. So this is fine. The same thing we have to do for this one as well, I believe. Yeah. Now this has to work correctly. Let's check the same. Let me run this one. Yeah, these errors are gone. We are left with one error. Mm, this is warning, right? So let's ignore this one. Let's go with the error. What is the error? Cannot find the symbol. W it is showing actually. Line number 70. We haven't initialized W or what? Mm, While position of x less than W of x dot size we are going with. Right? So let's check the initialization. Right. So position of x we are going with. This is fine. Yeah, we are going with the this one, right? V of this one. V of x I have given. So W, there is no W at all. So that is the reason. We are going with V, not W basically. Let me run this one. We are getting -1 by, we have to get the output 3, right? For the second one, we have to get -1. Let's check what we have done wrong. So what mistakes I have done here is, so in the line number 51, so here we are going with x comma y plus n l plus l, this one bitwise and 1. So this has to be accordingly with what this one we are going with, the approach we are going with, it has to be r minus r bitwise and 1. If it is equivalent to 0, then we have to print 1 else 0, right? So this one is one of the mistakes. And here in the line number 73, this has to be if n are greater than or equal to L, actually not 1. So this is fine. Uh, these were the two typos. Let me run this one now. I hope this works. Yeah. Now we are getting the output 3, which is absolutely correct. Now let's do one thing. Let me copy this one. The output that I need to get here is -1. Let's check the same here. Yeah, we are getting the correct output. Let me copy this one entirely. Let me hit the submit button here. Let's wait for some time. Yeah. Let me paste the code and hit the submit button. I hope this works for all the test cases. Let's see. Let's wait for some time. Running on 25, 30. Let's wait for some time. Yeah, you can clearly see here in the toast it is showing accepted. The verdict that we got here is accepted, right? So we have made use of pure this thing here, Dijkstra kind of thing, right? Parity states. We went for the checking parity states. This one approach we can call this one, right? Which similar to the Dijkstra kind of thing, right? So this is fine. Now I hope the solution part is completely clear. Parity checking. This one, you can clearly see here. I hope the solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.